How do you know these are from Mars?
Well, originally they were kind of an oddball group back in the day. In the 80s, there were sort of a handful of these meteorites. Now we have 200. Somebody had the bright idea to look to see what kind of gas might be trapped inside these rocks. And it turns out that gas matches the Martian atmosphere, and we know that from the Viking landers that sort of landed and didn't send anything back, but they analyzed the data.
Right.
So it's a 1-to-1 match. So that's kind of a fingerprint for these rocks being from Mars, and then the rest are sort of linked to them by chemistry.
So how do these meteorites end up on Earth?
Something has to hit the surface of Mars. It's the sort of thing where they originally said it couldn't be done, but then that sort of chemical fingerprint was discovered, and then the physics had to be worked out. So the models now tell us that some asteroid, probably from the nearby asteroid belt, has to hit the surface of Mars and explode, make an impact crater.
Right.
But near the point of impact, rocks right near the surface get kicked off. They get blasted off the surface, accelerated fast enough to leave Mars' gravity.
So it chips a piece of the planet off.
Yeah,
And off
yeah.
it goes, yeah.
Yeah. So we think this has happened about 10 times total in recent history, in the last few million years, to
Recent history, says Chris.
Well,
Last
it's
few
recent.
million.
Yeah, exactly. I mean, the rocks themselves are much older. So,
Okay.
the last few million years, we've had sort of 10 events that have produced these 200 meteorites.
Okay. Now, you brought these with you. These are kind of cool. These are kind of little slices of them, right?
That's right.
So can you describe these for our listeners? What do we see?
Sure. I mean, they're not a whole lot to look at. I mean, the Martian meteorites predominantly are lava flows. So think of, Hawaii or someplace like that, where you have a lava flow down the side of a volcano. And so there's fairly small crystals in them, et cetera. But the other thing that we have in there are these little veins and little black pockets and things like that.
Right.
That's from the shock, basically, that they experienced when they got ejected from Mars.
I see.
And so that's a key part to this whole story, is actually figuring out what are the conditions of that shock ejection that allows us to link it to a specific crater.
Yeah, so you have determined exactly where on Mars this came from. How did you pinpoint that?
It's been a long process. I started 7 years ago.
Not millions years. Oh,
no, but long still. But it's a process that involved a lot of colleagues from around the world, because what we basically said is okay, you've got 10. We're looking for something like 10 craters in the last few million years. So you're looking for nice fresh craters, relatively recently formed, apparently, on Mars from remote sensing.
Right.
But there's hundreds of them.
Yeah.
Right? I mean, there's millions of craters. So there's sort of hundreds of possibilities. Then we say, well, let's narrow it down to those places where there's lava flows. Like Tharsis and Elysium are the big igneous places on Mars.
Yeah.
And then narrow it down further and further. And then with some sort of sort of updated physical modeling, we can narrow it down further. So it's sort of like a process of elimination. Mm-hmm. And what we did was we ended up with 15 potential craters for these 10 events.
That narrows it down pretty good.
And so then we could go from a specific information in a meteorite like that to the specific conditions and ages, et cetera, of the crater and the surrounding area that the crater sits on. Mm-hmm. And we've been able to do that for 5 of them. Our study shows that we've been able to do that linkage for 5. So we're halfway there, essentially,
right,
to figuring out where all of the Martian meteorites come from.
Now, I'm always curious when you study a planet like Mars for as long as you have, like when someone shows me a map of a lake and it's in Alberta, I'll go, oh, that's Sylvan Lake. When someone shows you a crater on Mars, do you go, oh, that's such and such? Do you know the planet really well now?
Well, I mean, I've come at it from the samples. So if you show me the sample, I could tell you probably what it is.
Yeah.
But I mean, that's where a lot of this collaboration with colleagues comes in, and
Yeah.
people who really know that, and been able to, and former students as well that have done mapping
Yeah.
of the surface. So it's been a really sort of a multidimensional study. So it's very satisfying to see it finally out there.
So does this change anything about what we know about Mars and its geology?
Well, yes and no. I mean, what happens? See, the thing is that process of ejecting meteorites from Mars, the natural delivery mechanism, is very violent. So it favors the strongest rocks.
Right.
And what that means is young igneous rocks, nice interlocking crystals, not altered by water. So most of the Martian, 99% of them are a few 100 million years old. Okay, so you talk about old, but that's relatively recently. Whereas sedimentary rocks, the rocks that we look at for evidence of ancient life, mm-hmm. those are much, much older and probably weaker, and they wouldn't make the trip.
Right,
so we have this bias in the sample set. But that being said, we get a lot of really good information from these, and the potential is there. When we have a meteorite that we know the age from a specific location on Mars, we can use it kind of like a pinning point, like the Apollo samples did for the moon, to sort of say, okay, this is the age of that sort of igneous
Right.
unit, which we haven't done yet for Mars.
Now, you're not at the point where you can actually study, real samples that we've taken from the surface of Mars that are not involved in this sort of violent meteorite sort of thing, but you're working on it. So remind us how you're involved in that to bring Martian rocks back.
Yeah, so I'm on the NASA Mars 2020 Perseverance rover mission, which is going strong. We collected another sample last month, and the difference there is that again we're exploring the sedimentary rocks laid down by water. Those rocks that much older than the Martian meteorites, and in fact one of the criteria is to sort of not get a rock that looks exactly like a
Right.
Martian
You
meteorite.
want the different ones.
We want igneous rocks as well, but they need to be really old so we can compare. And essentially, if and hopefully when we get the Martian samples back from the rover that we're collecting in something like 10 years, it'll give us very complementary information to the Martian meteorites. So to total, we'll have a much better idea.
How are you going to get them back?
Well, that's still up in the air. So there was a plan, but sort of NASA's reviewing it because of the costs, et cetera. So that sort
You're
of
going
thing
to have
will
to
be
land
worked out.
something on the surface of Mars, pick it up, and that's going to have to launch off again. That's complicated.
That's
stuff.
complicated, yeah. Notionally, that we hand off our sample tubes, the samples that we collected in tubes, to another sort of lander that has a rocket on board that blasts them off the surface. So again, we've never done anything like that, so there's a bit of work to do there.